Okay, I've started the recording for the class. First thing, if you guys notice in the chat, there's a link there to a document. I've not tried that before, so hopefully that will allow you to have access to what I'm getting ready to show. Because I want to spend a little bit more time today talking about these literal equations. Because these are the kind of things that a lot of people struggle with, not just you all, but in general. Because there are patterns involved here. If you notice, problem number 1, that is a one-step equation. Because all you have to do is divide both sides by 6. Now, some people will say, well, I can't divide G by 6. That's okay. We don't know what G stands for, so we're just going to have to leave it as G over 6. And if you guys have gotten to the point in Odyssey where you're doing those problems that involve the volume, there's one problem in there where it talks about the volume of a vase, that they're filling 2/3 full with water. That is an example of a literal equation. There's a couple of other problems where they're talking about gift wrap of a box. That's also a literal equation. And so formulas typically fall into that category. They're mostly letters. So if you look down here at number 7, there's one that's got nothing but letters. U equals K divided by A, and you have to solve for A. Well, there's several steps you're going to have to go through there. But one of the keys when you see these fractions, things that look like fractions, is you have to think about multiples and think about the reciprocal. Does everybody know the word reciprocal? Well, that's okay. Very important term. Whoops, if only I could spell it correctly. That's right, Ariana. That is the opposite. The reciprocal is the flipped over version of a fraction. So if I have a fraction 1/4, the reciprocal is actually 4. But I can also write it as 4/1. Now there's a problem here that I'm going to demonstrate that's very similar to one of the equation problems that you'll see in Odysseyware. And it involves using the reciprocal. I want to go back to these literal equations here again for a second though. Like this one here, -3x plus 2c equals -3. Problem number 10 there, it says solve for x. Don't have to use any reciprocal on that one. But part of the reason why we have to know how to solve these literal equations is because what's coming in the future, -3x plus 2c equals -3. If I'm solving that for x, what's the first thing that I'm going to do? Anybody have any idea?
Divide -3 both sides.
Yeah, somebody said add 3. Somebody else said divide by -3. You could do either one of those, but adding 3 leaves you with 0 on the right-hand side. That doesn't really help you, because then all of your terms end up on the left. Dividing by -3, you're probably going to have to do that eventually anyhow, so that's not a bad thing. It's not necessarily what I would do. There's something, I don't know if I mentioned it before, but I'm going to talk about it now a little bit, this idea of move and divide. When I talk about moving, what I'm really talking about is canceling. When we have talked about equation solving, it's a lot of times it's been, well, let's just leave the variable that we're trying to find to last. Deal with that last. Well, what that forces us to do then is to deal with this 2c term. I'm not sure, was it Jonathan? Was that you that said divide by -3?
Yeah.
Okay, let's go ahead and do that. Solving for x here makes this positive. -3 divided by -3 leaves me with x minus, this becomes a fraction, minus 2/3 equals 1. Now that's kind of messy. Oops.
Would we still,
2/3.
sorry, okay, I was going to say, would we still have the C?
Yes, we do. Yeah, we do. Sure enough, good question, good observation. You guys are getting better at catching me on my mistakes. I appreciate that. You got to be able to do that, because that shows me that you know more about this stuff than you probably even know yourself when you're observing that and calling me on it. The only thing that's different here than what I would have done is the order, because now I got to add 2/3 C to both sides. No big deal. Because now you see x is positive 2/3 C plus 1. Now what Jonathan suggested was do the division first, and it works just fine. It's the great thing about math. There's always more than one way to solve these problems. And it really comes down to what you prefer, what you see. Because for me, I like to get rid of that other term and leave the variable for last. But I'm not going to dictate that to you, because that might not be how you see the problem.
So x equals 2/3 C plus 1 is the answer?
That is the answer. The only difference here in what I'm doing is I'm getting rid of that 2C term first. Whoops, I don't need 2 minus signs, just 1. Because here it's going to cancel on the left. And I'm still going to end up needing to divide by -3. Now all my terms are negative. So once I do that division, I'm going to end up with the same answer that we did doing it the other way. X equals 2/3 C plus 1. Same exact answer, two slightly different approaches. And it really, like I said, it really just comes down to what you prefer to do, how you see the problem developing. Now, part of the reason, a big reason why we have to know how to do these literal equations and we have to understand these procedures is because when we start graphing, which is in the next unit, this is actually sort of in the format of a standard form equation. And standard form equations are hard to graph, but if we can convert them by solving for one of the variables, it becomes easier to graph. So understanding at some level this process to solve, to rearrange the terms, because that's all we're really doing. We're just manipulating these equations now to rearrange the terms to get to the one that we want all by itself. Anybody have questions about any of that so far?
No, it's clear.
All right. Now here comes the big one. This is similar to a problem in Odyssey where almost everyone has gotten wrong the first time through. Now, I'm using different terms here. My numbers are different, but it follows exactly the same pattern of the problem in Odysseyware. And it's on the quiz. Some of you may have been, it might have been reassigned already. One of the things I've tried to message people about on that problem is, let me back up here for a second. This is the problem that asks, simple, sounds like a simple question. Are these equivalent? How do you know? Part of what I've been trying to say to people that are working on this is where you have to think about multiples and how do we deal with these fractions. We've got to be able to find some way to eliminate these, because I could subtract 3/8 here from both sides and end up with 5, 6x equals something, 6 minus 3/8. That's kind of messy. And the other thing is both of these fractions they don't have the same denominator. I don't like that. Nobody likes fractions. I know you guys have told me you don't like fractions. That's okay. So there's two things you can do here. This problem is a one-step equation. This one's easy to solve. There's no mystery to this one. You're going to divide both sides of that by 20, right? We need to get the x. 20 divided by 20 is 1. So if you do that first, you know that x equals 6.75 or 6 3/4, 6.75 if you do it on a calculator. So what I'm looking for is the same answer in the other problem. I need if x is equal to 6.75 on the other problem, then I know that these equations are equivalent. So where do you start on the other one? Anybody have?
What if I took 6.75 and put it in the x in the another one?
Oh.
To show,
okay.
To show if the equal 6 right, that means right.
Was that a Nur or Nura?
Nura.
Very good. That is definitely one way to do that. You are talking about doing substitution. The only bad part about that is you're still dealing with fractions, and some people still struggle with how to multiply fractions. Remember, with fractions, we multiply straight across. The numerator against the numerator, denominator against the denominator. And some folks have a hard time seeing that 6.75 over 1, let me see, where's my line? There we go. There's the fraction for 6.75. If you're going to use the fraction, that's what it would look like. So 5 times, and I'm going to recreate these fractions here in a second. So don't call me out on any wrong answers yet. I'm working up to it. One. That also equals a fraction. So now you got the multiplication set up. We still have this as a fraction, 3 over 8. What is 5 times 6.75?
54.
Okay. So that is 54. Now divide that by 6, because once you do this multiplication, you got to multiply on the bottom. So you have 54 over 6. So that is 9. Okay, we're almost there. 9x plus 3/8 equals 6. Still kind of messy though.
Yeah, it's so long.
So that's one approach. I'm going to just leave it at that for the moment. Anybody else have another idea about how to approach solving that one on the left?
Subtract 3/8 from both sides.
Okay. Now that might even be worse though in some ways. What do you get when you subtract 3/8 from 6? See, that's the problem. As long as you're still working with these fractions, it's messy. How can I clean up these fractions from the get-go? I'm gonna rewrite my problem here, and because what I've been trying to lead you guys to on this problem is to find a common denominator. Some people have done that. Common denominator means what multiple does 6 can I use with 6 and 8 to get to the same number?
2.
No, not division. You're factoring. That's the opposite. I need higher numbers. I got to get a higher number. If you think about multiples, 6, 12, 18, 24, 30. These are multiples. 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5. I could keep going. Now with 8, I got 8, 16, 24. There's my common multiple. 24 is the number that works for both of these. So if I multiply both sides of this equation by 24, I'm going to get rid of all these fractions. Okay? So when we have this 5/6 here, what's 5/6 of 24? 24 times 5, 120. 120 divided by 6 is 20. Now I can factor. 6 goes into 24 4 times. 4 times 5 is 20. Now this is where, Ariana, you were telling me about doing your distributive property. This is where you have to do that also. 3/8 of 24. 24 times 3, 72. Divided by 8 is 9. Oops. That's supposed to be 20x there. Plus 9. Equals 6. But I'm not done yet. Can't just leave this 6 here. I got to multiply that by 24 also. And over on that side, I get 144. So when I rewrite this, 20x plus 9 equals 144.
144 minus 9.
Right. And if you notice, one of my original problems here, I had 20x. What's going to happen when I take away 9? 20x equals 135. Same as the other original problem. I didn't even need to solve it for x because now I have both of these in the same format. 20x equals 135. 20x equals 135. Seems confusing, I know.
Yes.
That's probably the most difficult problem that I've seen everybody struggling with, or a lot of people struggling with in his first couple of lessons in Odysseyware. So just think about multiples.
I
Question?
can't understand why we choose 24. Why we go to this step.
Okay. I'm trying to get rid of these fractions here. See my list of multiples up here, 6, 12, 18.
Okay.
How do we add fractions? We have to have a common
Yeah.
denominator, right? If you look over here, 5/6 in this format and 3/8 here, those do not have a common denominator. So I'm trying to get a number that they both will go into, that it's going to allow me, in this case, to actually eliminate the fraction, not just make a common denominator. I need more room here. So I'm going to go back to adding fractions here for a second and show you why I picked 24. So down here in this corner, I have 5/6 plus 3/8. How am I going to add those fractions together when they don't have the same denominator?
5 divided by 6 times 2.
Oh. Uh-huh.
This is where the multiples come in. If I take
Mhm.
6
Yes, yes. Now I understand.
times
Yes.
2 times 3 times 4, that gets me to 24. I can convert this. If I multiply this fraction by 4/4, anytime we're converting fractions or trying to eliminate fractions, if we're using something that will allow us to cancel, or with just adding fractions, we're gonna change how the fraction looks, making the parts different sizes, but it still means the same thing. It's an equivalent fraction. If I multiply this one by 4/4, that's the same as multiplying by 1. 3/8, I have to multiply that by 3 to get the
Yes.
denominator up to 22.
Yes. Now it's clear. Yeah.
Okay, good. And that problem that's in Odysseyware has different fractions, but it's the same kind of idea. We're looking for some multiple that will work for both, that will allow us to get rid of the fraction.
Okay.
Now, part of the reason for that, another reason, another reason to think about those kind of processes is this, like problem number 17. We want to get rid of that our variable is tied up in a complex fraction. So we want to get rid of that first. So this doesn't necessarily involve a multiple, but it just involves multiplying by the denominator. So that's a little bit simpler. If we multiply both sides by -16, our fraction disappears. And this works for every type of equation that you're trying to solve. And I'll show you why. So that problem, n plus 5 over -16 equals -1. So again, if I'm multiplying, I'm going to show this as -16/1 because that doesn't change the fact that it's still -16. If you think about this as a quantity that you're multiplying the -16 against, well, now the -16 is in both the numerator and the denominator. We have one on the top, one on the bottom. What's -16 divided by -16?
0.
Division, not subtraction. It's 1, yeah. Anything divided by itself is 1. That's why we do this kind of process to get rid of the fraction. Because now we just have 1 times n plus 5. And that undoes that complex fraction. It eliminates it for us. Here on the other side, it's just -1 times -16. Once the fraction's gone, it's easy. N equals 11. Questions so far? All of these up to this point have been two-step equations. Now, what follows that in Odysseyware are two-step inequalities. Two-step inequalities. Let's see, anybody remember what our options are for solutions with equations? There's three possibilities. Anybody remember one of them? It's okay. Remember, if you're not comfortable saying it out loud, you can always put a response in the chat, and you can just send it to me individually, so no one else has to see it. Think about it. What is x when we say 6x equals 18? Well, it's 6 times x. There's only one possible number that will allow that to equal 18 when you multiply 6 times a number, 6x. Well, there's one answer for that. That's 3. All right, good. Somebody's doing it. Thank you.
I accidentally sent that late. I was trying to send it while you're.
It's okay, good. So there's one answer for most equations. Now, we can also have an infinite number of solutions. Remember, if all of our variables are eliminated, we watched the Odysseyware video on this the other day. If all of our variables are eliminated, we can have, and we get a true statement, that means we have infinite number of solutions. So no matter what you put in for the variable, you're going to get a true statement. What's the third option? One solution. Infinite solution. Nobody remembers the third option? No solution. Think about this. 2m equals 2m plus 2. That's a two-step equation. The only difference here is we have a variable on both sides of the equal sign. And we need to get them together. What happens when I subtract 2m?
M 2.
They cancel. This is what I mean about a true statement or not getting a true statement. Well, what's 0 times m? It's 0. Does 0 equal 2?
No solution.
No, not true. This is no solution.
Okay.
No solution. But that's with equations. One solution, infinite solutions, or no solution. Now, if I had 2m equals 2m, and just for demonstration purposes, plus 0, I do the same thing, and I end up with 0 equals, oops, I subtract 2m from both sides, and I end up with 0 equals 0. Now I have a true statement. That's infinite solutions.
Mm-hmm.
All my variables still got eliminated, but it's now a true statement. So what we're about to go into though now with inequalities is something called a solution set. And we have to start graphing these things in different directions. Sometimes we're going to put an open circle on the end of a line. Sometimes we're going to put a closed circle on the end of a line. Later on with compound inequalities, you might have two of these on the same graph. So this is the first, with these inequalities, this is really the first time we venture into graphing. The nice thing about these kind of problems though is you solve them exactly the same way. So if you look at how this is structured, 2x plus 4 greater than or equal to 24, that's just a two-step equation. We still got to solve for x. No different than we were doing with the equations. But once we graph it, it's going to look different. So if I go back to my whiteboard, the other thing that you have to get used to here, I guess I'm gonna have to. We have 4 symbols that we have to learn how to use. One pointing to the left is less than. If you're on a number line and you go to the left on that number line, what happens with the numbers?
Less.
They get less, they get lower. They go into the negatives if you go far enough, right? The opposite is true with greater than, right? You go to the right, the numbers get higher.
More.
Whoops, that's not what I want. You might have seen in grade school, or maybe even some documents around here, these symbols made to look like alligator teeth. The reason for that is those symbols are gobbling up the bigger number. Doesn't matter which way they point. The bigger number is always on the open side of the symbol. The lower number is on the point. Okay? On the point is always the lower number. Now, the other thing that we have to get used to, the other two symbols, once you add this extra line here, this becomes equal to also. So we would say less than or equal to. For the one on the left, greater than or equal to on the right. And they graph differently. And this is a big deal. So if we're graphing these that just say less than or greater than, these both have this open circle on the end. These though, and this is true throughout every level of algebra or geometry that you go to, you're going to see these open and closed circles. The open circle means it's not included. The closed circle means it is included. So if I go back to my original example with an equation, and sometimes this really gets people confused. 3x equals 18. Divide both sides by 3. Your answer is going to be one and only one answer, x equals 3. But now, let's see, I don't know if I can do those angles. Now, if I do 3x less than 18, 3 is still the solution, but it's not included. If I were to graph this on a number line, I would start at 3 and have an open circle and go to the left. Because when I plug it back in, oh, and I did my math wrong, this should be 6. Come on, you guys, you gotta bail me out here. Let me back up here. 3x equals 18. X equals 6. 3x less than 18. X less than 6. So on a number line, that's 0, 5, 6. Start with the open circle. And you go to the left. That's the answer for that inequality. But if you plug 6 back in here, 3 times 6 equals 18. It's not less than 18. So that's why the circle has to be open. You cannot include it. When you do the other though, 3x, 3x less than or equal to, hang on just a second, Autumn. X less than or equal to 6. My number line is going to look exactly the same. My answer is still involves 6. But now I have a closed circle at 6. Because now it's either 6 is included. Okay, Autumn, what's your question?
Does this get recorded, like the whole Zoom meeting, so that I can come back and reference it if I have to?
Yes. Yeah, I usually wait to the end of the week to put them up on my YouTube channel. But they do get posted usually on Fridays.
Okay, thank you.
You bet. Okay, so we start looking at some of these problems now. Now you got more things to think about. The process to come up with your answers though for X or M or whatever the variable is still the same. Two-step equation here, probably going to subtract 4 from both sides to begin with and divide by 2. Do that first one, 2x plus 4 greater than or equal to 24. A lot of distributive property problems in here. In fact, I'm going to pause this for a second and give you guys access to this also in the share, in the chat, I mean. Okay, so I've added that two-step inequalities worksheet into the chat. You can download it and play with some of them if you want to, or just use it for more practice. And you're going to notice that you're going to see some very similar format problems that as you've already seen in two-step equations or even in multi-step equations. You've got some
So
fractions.
all the answers will have to be graphed.
Typically, yes. But the graphing part isn't that tough once you figure out the answer.
Right. I was just making sure.
Yeah. Yeah, if we were in the in-person class, everybody would be working on probably the odd number ones here and then turning it in for a grade. If you got the right number, but you didn't graph it, you would lose a point. You know, like these would be like 2-point problems. If you solve it correctly, that's 1 point. Graphing it would be a 2nd point, maybe even 3 points, because now with the open or closed circle, you've got these style considerations to think about. So I'll show you how similar this is to all the equation solving stuff that you've already been doing.
So basically, if it's a less than or equal to, it's a closed circle.
Yep. Because that means that the number is your solution number is included.
Okay.
So here's how I would do the first problem on there. Again, I'm using the move and divide, move or cancel. 2x greater than or equal to 20. Divide by 2. Divide by 2. X greater than or equal to 10.
Cool.
So I got X is greater than or equal to 10. And so when I have to go back to the other sheet to graph it, there's positive 10 on the graph. I would put a closed circle right there. I don't have any way to draw on this, unfortunately. And my arrow would be going to the right, because now all the numbers that are greater than this are part of my solution set. And that's the big difference with inequalities compared to equations. We have a whole range of answers. It's not just one answer. It's not just no solution or infinite solutions. We're starting at some place on the number line and we're going in one direction or the other. And if you're not sure about your answer, pick another number and plug it back in. If you're not sure about which direction your graph line should go, what if we put it over here? What if we said 3 is a solution? So 2 times 3 is 6 plus 4 is 10. Is 10 greater than or equal to 24? No. So you would not put that graph line going in that direction. Plugging it back in over here, if you put in 20, 2 times 20 is 40 plus 4, 44 greater than or equal to 24. I know it's not on the graph, but you can visualize that your number line going to continue infinitely, and so your graph line would go to the right also. Now, there's one big thing here that makes these inequalities tricky. There's an extra rule. This is the next problem I'm going to do here, number 3. -3 times this quantity, p plus 1, that's a distributive property problem, is less than or equal to -18. -3 p plus 1 less than or equal to -18. And we're still following PEMDAS. So I can't solve the parentheses necessarily first, but I can do a simplification by applying that -3 against each of those terms. I get -3p minus 3 less than or equal to -10. I add 3.
18.
Oh, 18. Yeah, I can't even read my own writing. Thank you. I wasn't going to come out right, so I'm glad you said that. I would have figured it out eventually. Add 3 to both sides. Now I get -3p less than or equal to -15. Here's where the big difference comes in at this stage. And this is a special rule that only relates to inequalities. When you divide or multiply by a negative number, you have to reverse the inequality. You change the direction of the inequality symbol. So when I divide both of these by -3, and I remember that rule, that's the first thing I do. When I go to the next step, I rewrite the symbol so I don't forget. I got to do that. Those cancel to 1. P is now greater than 5, greater than or equal to 5. If you don't do that, your graph line is going to be going the wrong direction.
It's not greater. It's
What?
the answer B. It's less than 5. It's not greater.
No. It's greater than or equal to 5. This is what I'm talking about with the rule. When you divide or multiply an inequality by a negative number, you have to reverse this inequality symbol. This changes direction. And here's why. If you don't, if your answer is P is less than or equal to 5, we're going to test a couple of answers on the number line. I'm going to use 0 to test this one here. P less than or equal to 5. Okay. So -3 times 0. I'm going back to the original. Plus 1 less than or equal to -18. So 0 plus 1 is 1. Is -3 less than or equal to -18?
No.
No, that is correct. It is not. This is closer to 0 than the -18, so that means it's greater than. So if I don't change this, I'm going to get an incorrect statement. And this one would graph in this direction. So it would seem to say anything less than 5 is okay. But 0 is less than 5, and that doesn't work. So now I'll go back to the other one. I'm going to pick 10. I'm going to use 10 to test this one. -3 times 10 plus 1 less than or equal to -18. If you notice, I'm solving the parentheses now because I have all numbers. 10 plus 1 is 11. Negative 3 times 11, negative 33. Now I have a true statement
Okay.
because negative 33 is farther away from 0 than negative 18.
Mhm.
And so there's two reasons that I'm emphasizing this. Obviously, your calculations might be all correct and you could get the correct number, but if you don't remember that rule, your graph's going to point the wrong direction. And with inequalities, that's the only time you're going to see that. But it is a special case rule that you really have to pay attention to. And you'll see a lot of problems on this worksheet that are like that, because this one's got a negative b. This one's going to have negative 4n. This one's going to have negative 4x. So anybody have any other questions about any of that today? Hi, Ebony. I didn't know you got on there too.
Hi, how are you?
Good, thank you. Don't really have anything else at the moment. You're going to see things like this in your Odyssey-ware as you keep moving. So hopefully that little extra explanation has been helpful.
You said the worksheet was in the chat.
The link, yes.
I don't see it.
I don't see it either.
Me too.
Oh, I see.
Right here.
Nura Mari got it, but I should have sent it to everyone.
Yes, I see it.
Okay, now.
There we go.
Okay, all right. Sorry about that.
I have a question here.
Okay.
How I can know I finished my assignment for this week? I started, but when I finish a step, let me go to another one and another one. I don't know what I have to do to complete the assignment weekly assignment, sorry.
Well, the Odyssey-ware assignments all are connected with due dates. And all Odyssey-ware does is it takes the number of assignments, spreads it out over the amount of time that we have in the term, and then assigns due dates. I don't really pay a lot of attention to those due dates unless somebody's really getting behind. So you can work as fast as you want to. If you find that you're not able to move on, it's probably because I haven't opened up the next assignment. If you need me to open up an assignment, you just need to text me. That's all. I just need to know that you're ready to keep going. I'm not going to slow anybody down. If you can work faster than what we're doing in class, by all means, go for it.
Okay.
Okay? But if you get stuck or you get blocked on something, that's when you need to text me. Let me know.
Okay.
I had a question.
Okay?
In my English class, my English teacher explained that the way that you get a grade in Odyssey-ware, but she said that her personal grade for us isn't based off of the grade that we get in Odyssey-ware, that it's basically the grade that she gives us is just based off the quizzes.
Okay.
How is our grade measured in your class?
It's strictly off of Odyssey-ware. You'll notice as you're making progress, it will tell you the percentage complete. There's a couple of different percentages that show up in Odyssey-ware. One is the percentage complete overall. The other is percent complete of a particular unit. The score is your best indicator of what your grades could end up being. Once a week, I transfer all this information to Synergy. And so the information I have in Synergy is not complete until we get to the end of the term. But as long as your score if you could continue to do the work and get those same kind of scores, you can expect that to be your grade. Got to complete everything. Of course, if we get to the end of the term and you haven't completed something, I'd have to enter zeros, and that's going to drop your grade. But I'm not using any outside stuff at this point beyond OdysseyWare. Now, that's probably going to change in the future as we go to Google Classroom. But that's not this term. That's in the future.
Okay, that makes sense.
Any other questions? All right, gang, I'm going to let you go. And I'll be around tomorrow. So if you get stuck on something or need some extra help, send me a text. Again, text from the phone is going to get my attention better than anything else.
Thank you.